Okay, today I will talk about the, the conformal model of the 3D space. And in fact, this presentation is motivated by the work, as Marcia mentioned, that we develop about protein structure calculations. Because we are using this conformal model in order to provide a different way to represent the protein structures. And the conformal model will be motivated by the properties of isometries. And we'll see that the conformal model presents nice mathematical properties of isometries that cannot be obtained when we use the, let's say, the traditional way to represent the isometries. So I also have to mention that this is a joint work with Michael Souza, is a colleague from Brazil, from Federal University of Ceará, and José Luis Aragon from UNAM in Mexico. Okay, this is the plan for our presentation, and the core of the presentation is related to these four points. And if I have some time, I can mention some things about the item number 5 and 6. So before we call in the definition of the isometries, let's remember that the Euclidean model of the 3D space is the vector space R3 plus the usual inner product that are characterized by these properties. As you see in the conformal model of the 3D space, we'll change the positivity.
Sorry, I have to interrupt you.
Yes.
The slides are not moving.
Are not moving?
No. Could you, are you still in full screen mode with your slides?
Yes.
Just leave full screen mode because it's not being displayed as full screen mode anyways. Okay, now it moved.
Yeah. Okay.
Yes,
okay.
now it's working. Okay.
Okay. So
thanks.
Did you see this, the table of contents?
We didn't see this, so maybe
okay,
just show it for
a bit. Okay. I was mentioning that the plan of the talk is related to the first 4 points, and if I have time, I can mention item number 5 and 6. And before recalling the definition of isometries, I mentioned that the Euclidean model of the 3D space is just the R3 plus the usual inner product that is defined by these properties. As we see in the conformal model, we will change the positivity of the inner product, but we will maintain the first 3 properties that are fundamental properties of the inner product. Okay, remember that what is the definition of isometry in the R3 is a function that for each pair of vectors of points in R3, the distance are preserved, where the norm here is defined, is induced by the definition of the inner product that I just mentioned. An interesting property of isometry is that we can represent isometry by an orthogonal transformation up to a translation. Okay, so we can describe an isometry by this expression using a matrix A that is orthogonal. And as we see, using the so-called homogeneous coordinates, we can represent isometry in the 5-dimensional space, where isometries can be represented in a linear way. It's like that we can incorporate the vector B that represents the translation in the matrix A. And since this matrix is orthogonal, I think it's a natural question if is it possible in the homogeneous model to incorporate the translation in the matrix A and also to maintain the orthogonality of this matrix. Okay, this is our motivation in order to develop the ideas. So let's consider this property of isometry, considering 2 isometries F1 and F2. If we calculate the composition of these 2 isometries, we obtain this expression. And if you calculate the inverse of this composition, we obtain this expression. using the homogeneous model of the 3D space, we can represent the composition just multiplying two matrices. And what we'll do using the conformal model is that we can also, we'll do almost a similar thing using just the inverse of the multiplication of matrices. So, and just remember, if you represent the 3D space using the homogeneous model, we can represent isometries in a linear way. And this is the matrix that represents the isometries. So what we do here is just to increase the dimension. So we are working in R5, and we fix all the coordinates related to dimension 4. Okay, this is an illustration of what is the homogeneous model. So we are representing here the 3D by this plane, of course, in order to visualize the 4D. And this new vector E4 is the additional dimension that we use to represent a point X in the 3D space. So since we can represent isometries of 3D space in 4D, we can represent isometries in a linear way, and the idea is to consider in 5D a copy of the 3D. And the question that I mentioned is it possible to represent isometries in an orthogonal way in the homogeneous model? Okay, this is the first question that we will answer. So let's discuss a little more about the homogeneous model. So E1, E2, and E3 are the canonical basis and orthonormal basis of the 3D dimension space. And we consider E4 a vector orthogonal to this canonical basis. So another property that can characterize orthogonal transformation in the 3-dimensional space is this equation, which means that for each pair of vectors in 3D, A will be an orthogonal transformation if the inner product, when we apply to UV, is maintained. So because of this property, now we will make our most important assumption that will motivate the next slides. So let's consider X, Y, two points in the 3D, and big X and big Y are the representation of these 2 points in the homogeneous model, so in the 4-dimensional space. So if there is a constant K different from 0, where this equation will be satisfied for every pair of points in 3D, this means that the isometries in the 3D space can be represented by an orthogonal transformation in the homogeneous model, okay? Because on the right, we will maintain the distances, so we have isometries, and on the left, we will maintain the inner product. So if we can solve this equation for each pair of vectors x, y, which means that if there is a k different from 0, it means that the answer for the question that I consider, that is it possible to represent isometries in 3D in the homogeneous model? Okay, if I can solve this equation, the answer will be yes. So the first consequence of, if we consider that this solution can be solved, is that the norm of the points, of the representation of points in the homogeneous model will be norm equal to 0. This means that the positivity of the inner product in the homogeneous model, in our case in the 4D, is not satisfied anymore. So this is an implication if you want to solve this equation. And this is why I mentioned when I remember the definition of the usual inner product, that we will change the positivity of the inner product. Okay, let's consider a more general representation of a point X in 3D in the homogeneous model. In our first case, I'll consider that the value of X4 is equal to 1. So in order to analyze algebraically, let's consider this more general representation. And what we do now is to use this representation in the homogeneous model. I will just replace in this equation. So doing the calculation, we obtain the following. Remember that we are maintaining the other properties of the inner product. That is, means the bilinearity of the inner product will be maintained, okay? So just doing the calculations, we obtain this equation. And since E4 is orthogonal to the canonical basis, we obtain this expression. So if we consider that the norm of the representation of points in 3D in the homogeneous mode is equal to 0, it means, and if we consider that we are not considering in the 3D the origin of the space, it means that the norm of this additional vector associated to the 4th dimension will be negative. Okay, so this is a consequence of our first equation that we want to solve. That will mean that isometries in 3D will be represented in 4D using the homogeneous model by an orthogonal transformation. Okay, now we'll define, just to simplify the notation, we'll define the constant psi, a positive constant psi, by this product, which means that the representation of a point X in 3D in 4D will be given by this. Remember that our first equation, in order to solve our first equation, we have to calculate the inner product of big X and big Y. Here I using just this representation that we will obtain as a consequence of norm of vectors B equal to 0, and we obtain this expression. So remember that this is the main equation, this is the fundamental equation that we want to solve. So we want to obtain the value for K that must be different from 0. And using this expression, we obtain these equations. And remember that all of these points, X and Y, are points in 3D. Okay. If we consider 2 points, X and Y, different, but linearly dependent by Cauchy inequality, the left side of this equation will be 0. And since X and Y are different, this implies that the K will be 0. So this is a contradiction. So this means that this equation cannot be solved for all pair of points in 3D on there, which implies that using homogeneous model, even considering that the positivity will not be any more satisfied, is not possible to represent isometries of the 3D space in the 4D. Okay, what we'll do now? Now we will increase one more dimension. So we start in 3D and we increase another dimension. We consider 4D and we use the homogeneous model to represent the 3D space. Since in 4D it's not possible to solve our equation, we'll consider another dimension. So let's consider the 5-dimensional space. So we'll do exactly the same as we did in 4D. So now we will represent a point X in 3D in the 5-dimensional space, which means that we have to calculate the coordinates of the new vectors E4 and E5. Okay. And we will use this new representation of a point X in 5D, we will apply in the same equation that there is a consequence of our fundamental equation. So doing the calculation and using the fact that the norm of E4 is equal to 1, because now I'm considering that E1, E2, E3, and E4 are a canonical basis, but in 4-dimensional space, which means that the norm of E4 is equal to 1, we obtain again a consequence similar to what we obtain in 4D. So if you want to solve this equation, we again obtain that the norm of the additional dimension related to the vector E5 must also be negative. So just to simplify the calculation, let's try that this, let's suppose that the norm of E5 is -1, okay? And remember again that in the 5-dimensional space, the points that we represent, the points in 3D must satisfy this equation. That is, the points that we represent, the 3D, must have norm equal to 0. Because of this, we will change a basis, this new basis. Why? Because the norm of E4 is equal to 1, and the norm of E5 is negative. So I would like to have this new basis also representing points of the 3D space. And in order to obtain this, they must have a norm of 0. So I will just change of basis. In order to do this, I will want just to solve this equation, which means that there are many possibilities for the coefficients of E4 and E5. So let's consider just the simple possibility. So we'll define a new basis related to the 4th and the 5th dimension that we call E0 and E infinity, that we explain why we use this notation, that will be defined just by this. So we subtract E5 by E4, and we add E5 and E4. Doing the calculations, we obtain what we wanted. So we want the vector associated to the new dimensions, we want that they have norm 0. And now we obtain new vectors associated to dimension 4 and 5 with norm equal to 0. So now we are in the 5D space, and it's possible to present some kind of visualization. Remember that some slides that I already presented, I show a visual representation of the homogeneous model. How we did this? So we consider that the 3D space was represented by a plane, and we could visualize the 4D. So now we want to visualize the 5D. How we will do this? So first, we will represent the 3D space just by a line. But in order to obtain this kind of visualization, let's just consider now a basis E1 that will represent the 3D space, and E4 and E5. Okay. And again, using our basic assumption that the vectors in this new space must have norm equal to 0, I will use this representation for the big X, and again I will use the bilinearity of the inner product and the products and the properties that we already knew related to the norm of E4 and E5. So using these properties, we obtain these equations in related to the coordinates x1, x5, x4, and x5. What is this? This is, we have now just 3 variables, so we can represent in 3D. And this equation represents a right circular cone. So now we have some kind of visualization of how to represent the 3D space in the 5D space. So we start, so as I mentioned, we are representing the 3D space by just a line that we associated to the vector E1. So we increase one dimension and associated to the vector E4 with norm equal to 1, and this vector is orthogonal to E1. Sorry. So we have another vector associated to dimension 5, and now this vector has a norm equal to -1, and this is our cone. So this means that just to remember, okay, this cone is the solution associated to this property. So in this cone, we have the points in the 5-dimensional space that represent the points in the 3D space. Okay, and use the definition that we use in order to obtain a basis that also obey this property that they have norm equal to 0. We also can visualize E0 and E infinity. Remember that E infinity was defined just by adding E4 and E5, and E0 was defined subtracting E4 by E4, by E5 by E4. Okay, now we are almost there in order to represent, in order to give the conformal model of the 3D space. Okay, our main the fundamental equation that I mentioned, we have to calculate the inner product between the two representation big X and big Y of points of the 3D space. So in order to calculate the inner product, it's necessary to obtain the value between the inner product between E0 and E infinity. And just to simplify this value, and also to consider the same value used in the literature, we will do a little modification of the definition of E0. Instead of consider just E5 minus E4, we divide it by 2 in order to obtain the inner product between E0 and E infinity that gives -1. Okay, now we can calculate the inner product between big X and big Y using the properties that I just mentioned. This is the result. In this equation, if we consider big X or X equal to Y, and considering our main consequence of our fundamental equation, we obtain this equation. X0 is the coordinate of the point X in the 4D, and X infinity is the coordinate of the point X in the 5D. If we consider that the coordinates of X0 is equal to 1, we obtain the coordinates of X in the 5D. And this is the expression associated to the representation of a point X in the 3D in the conformal space, in the 5-dimensional space. So, and finally, using this representation, in order to calculate the inner product between big X and big Y, and using the properties that I just mentioned, we solve the equation that I proposed in the beginning. So here is the value of the constant K different from 0. Its value is minus 0.5. So this means that isometries in 3D can be presented in an orthogonal way in the 5-dimensional space. Okay, so in the 4D it was not possible to solve this equation, but in 5D is it possible? Of course, we had to change the positivity of the inner product. So now we can obtain the, let's say, the complete visualization of the conformal model of the 3D space. Note here that in this part, we have some kind of the representation of the homogeneous model because we have just one point and we add with the additional dimension. And this is the representation, this is the coordinate when we have to consider also the 5 dimension. What is this? So in order to represent the point X of the 3D, so we add this vector, and when we are here, we consider a parabola. So we are in a situation like this. So the representation in the 5-dimensional space of the 3D space is this parabola. In fact, this is obtained by intersecting a plane that is parallel to infinity with the cone. Very nice, huh? So now, just to resume, what is the conformal model of the 3D space? It's just the R5 with a new basis E1, E2, and E3 is our classical Euclidean space, and we have additional vectors associated to dimension 4 and 5, E0 and infinity, satisfying these properties. These are the properties that we in fact constructed. So the first equation is related to the orthonormality of our canonical basis. Equation 2 and equation 2 and 3 are related to the fact that E0 and infinity are orthogonal to our canonical basis. And the last two equations are the properties that we obtain in our development. So I mentioned that we use the notation E0 and infinity. In fact, there is a reason to explain this notation. And it's very easy to check that E0, there is a non-zero vector, but with a norm equal to 0, represent the origin of the 3-dimensional space. And E infinity, as the notation suggests, represent the infinity of the 3D space. We obtain this using the homogeneity of the conformal model, which means that these 2 points, these 2 vectors represent the same point. Okay, now I will give the matrix representation of the isometries of the 3D, but represented in the 5-dimensional space. And this is important because now we develop the theory, but in order to use this, for example, in computer graphics and in molecular geometry, it would be nice to have a matrix representing these isometries. And we'll see what are the changes necessary because the inner product in the 5-dimensional space do not obey anymore the positivity. Yeah, okay. This is the property that we use in the beginning. Yes, that the isometry is represented like this, and using the conformal model, we can represent these isometries using this expression. So is the point, in fact, this is the point after the application of the isometry. We consider the E0 representing the homogeneity of the model, and the coordinates of the 5 dimension is just to consider the square and multiplied by and divided by 2. So now, after some manipulation using linear algebra, we can represent this part by this sum. And here we can notice that we have the original point in the 3D space. Here we have okay, here we can notice the value, the number 1, and here is the coordinate of the point X in the 5D. We can organize this in this matrix form. So this is the representation in the conformal model of a point X of the 3D space. So we fix the coordinate, the fourth coordinate is given by 1, and this we consider the square of the norm divided by 2. So, and the last column is exactly the property that we obtain here. So this means that an isometry in 3D can also be represented in the conformal model by a linear transformation. But what we motivated, and we already known by the theory that we discuss here, is that the isometry must be also an orthogonal transformation. So we have to prove now that this matrix is orthogonal, considering now that the inner product has not the positivity anymore. Okay, we can represent the inner products between 2 points in the conformal model using also the matrix representation. And what we observe here, so this is the representation of a point X in the 3D in the conformal model. This is the same representation of the other point Y. And this is the identity now in the conformal model. This identity is related to the fact that when we consider, if we consider here the vector E0 and here the infinity, this -1 is -1 is represented the fact that when we multiply E0 by E infinity, we obtain -1. So this is a kind of generalization of identity in the conformal model. So using this matrix, we can try to calculate this multiplication, because it's natural to now include the identity in the conformal model. And doing the calculations, we obtain what we expected. So when we do this calculation, we obtain the identity, but now the identity in the conformal model. So, and finally, in order to prove that the matrix U that represent the isometries of 3D space, but now in 5D space, is orthogonal, we have also to calculate the square of this identity in the conformal model. And finally, when we apply this matrix U that represent an isometry to a point X, the big X that represent a point X in the 3D, we doing the calculation, so we multiplied by, on the left, by this expression. And since this first matrix results in the matrix IC, we multiply on both sides by IC, and we obtain this expression. So this means that the inverse of U, but now consider that this new kind, this generalization of the inner product can be given by this expression. So in fact, the only difference considering the orthogonality in the 3D is that we have to multiply on left and right by the identity matrix considered in the conformal model. But this means that the inverse of a matrix can also be obtained in a very easy way. We just transpose and multiply on the left and right by this new kind of identity. Okay, now I have more 7 minutes. Yeah. Okay. In 7 minutes. I think I can just mention the points 5 and 6 in our plan. So in the conformal model, we see that we can represent isometries of the 3D space by an orthogonal transformation. Another consequence of this property is that the spheres of the 3D space in the conformal model can be considered as basic objects. What is the meaning of this? So let's consider this vector. So C is a point in 3D space. Big C is the representation of this point in the conformal model, and R is a positive number. So this is in fact is a vector. Yeah, is a vector in the conformal model. If we consider another point, big X, And if we multiply big X by S, and using the properties that we already know in the conformal model, we obtain this expression, which means that if this equation is zero, this, in fact, this is the equivalent of this equation. This is the equation of a sphere center at C with radius R. This means that this object, that in fact is a vector in the conformal model, represents a sphere of the 3D space. So this is why I mentioned that the spheres is a basic object in the conformal model. So a sphere can be represented as a vector. And in fact, spheres and lines are the basic objects in the conformal model. So a point in 3D can be easily shown that is represented by spheres of radius zeros, because this term is zero. And we can also, after some calculation, we can also obtain that a line in 3D can be represented by a circle of radius infinity passing through infinity, and a plane in 3D can also be represented by a sphere of radius infinity passing through infinity. So as I mentioned, the basic object in the conformal model are spheres and circles. So now we can obtain a richer structure of the conformal model if we define a more general product in the conformal model. When we do this, we obtain what is mentioned, the conformal Clifford algebra. As I mentioned in the beginning, in the literature, the conformal model is presenting after the definition of the Clifford algebra, which is I think is much more complicated. Here we presented the conformal model using just basic properties of linear algebra, and the only thing that is different is that we change the definition of the inner product in a product where the positivity is not more satisfied. So when we define this kind of a general product in the conformal model, we can consider a unified framework for objects and transformations. What is the meaning of this? When we, in linear algebra, when we multiply a matrix by a vector, we have to take some care about the dimensions. Yeah. So we have different objects to represent the operator, the transformation, and the object where we apply the operator. Using conformal Clifford algebra, both objects will be the same nature. So what is formally how we can define a Clifford algebra on the conformal model? A Clifford algebra is just the vector space with a new kind of product of vectors that we call geometric product. This product is associative, is distributive, but is not commutative. Okay, and this new kind of product is defined by these equations. So the first equation is related to the orthonormality of the canonical basis. The equations 2 and 3 is related to the fact that E0 and infinity are orthogonal to the canonical basis. And the other equation is related to the fact that the inner product between E0 and infinity is minus one. And the last two equations are related to the fact that the norm of E0 and infinity has norm equal to 0. Okay, what is important from this definition that is of the Clifford algebra is that we can obtain the definition of the inner product that I present before when I define the conformal model. So in fact, the inner product can be defined by this general product by this expression, and another product can be defined using the non-commutativity of this new kind of product. So because of the non-commutativity of this new kind of product called Clifford product or geometric product, we define this new product called autoproduct. So both these products were defined by Grassmann, And what Clifford did was to put them together. So there is also using the inner product, we know that when the inner product between two different vectors, when they are zero, it means that they are orthogonal. There is also a geometric interpretation when we use the outer product. When the outer product between two vectors are zero, it means that they are parallel. So because of the non-commutativity, we can define another product and we obtain very nice geometric properties. So, as I mentioned, Clifford put together these two definitions of the products. If we add just two expressions, we obtain this equation that is called the fundamental equation of Clifford algebra. So this new product that we define, in fact, is an addition of our classical inner product plus the outer product. I'm almost there. We know that the inner product is a scalar, is a real number. What is object is this outer product. So if we square this object obtained by the outer product between IE and IJ, doing the calculation, we obtain that the result is -1, which implies that this new object cannot be a real number. So if we consider that this new object is a vector, and using the fact that the square of a vector is related to its norm, so it's greater than 0, so we obtain a contradiction because we already know that the square of this object is -1. This means that the outer product between E1 and EJ is not also a vector. So it's a new kind of object. We call it a bivector. So is an object with two dimensions, and we can visually see like a parallelogram defined by the vectors I1 and IJ. So in fact, we can also obtain k vectors. We obtain trivectors and so on, and the linear combination of all of this k vector is represented by a multivector. And if we consider all of this linear combination, we obtain a vector space of dimension 32. So we created a monster. Yeah. So, but this monster has very nice properties, better properties than the conformal model that as we see, we obtain new mathematical properties. But when we define a Clifford algebra in the conformal model, we obtain a more richer space. For example, in this space, we can calculate Euclidean distance in a more efficient way that is done using the classical coordinates. In fact, we are working on this conformal Clifford algebra in order to calculate distance in the 3D space, of course, because our interest is in the objects of 3D, but we increase the mathematical structure in order to obtain better properties and in this case, in this particular case, to obtain a more efficient way to calculate distances in the 3D space. Okay, just to mention that it's interesting to note that there is a patent related to the conformal model. And all the details of these presentations can be obtained in this paper that was just published. And I finalize here. And I thank you very much for your attention.
Thank you, Carlile. Very nice talk. So let's see if we have questions.
Thank you.
Well, Carlile, I have a question. Actually, I was thinking if you have used these conformal models,
yes,
applied to optimization problems and their solution. For example, the problems that use it for the configuration of proteins, or kissing number where we have to model spheres. Do you think this could be applied in a nice way to the solution of problems?
Yes, I can. And this is completely related to the fact that I mentioned at the end, that we can calculate distance between points in the 3D in a more efficient way. And how this is related to optimization techniques? Because when you consider protein, we have a function that and this function are related to the physical chemical interaction between atoms. And in this expression, all of these expressions are related to the Euclidean distance between points. So in order to evaluate the function, it's necessary to calculate the distance between all of the points. Of course, there are some, it's necessary some approximation, because, for example, if you consider big protein with 10,000 atoms, and if you want just to evaluate some kind of conformation, it's necessary to obtain, if you want a precise value, it's necessary to obtain all of the distance between each pair of these distances. So when we use optimization method, it would be nice to calculate the gradient and the Hessian, yeah. And when we calculate the gradient and Hessian, the core of the calculation are related to the Euclidean distance between all of the points. And in this point, and since we using the conformal model, we can calculate distance between points in a more efficient way. One of the things that we are trying to in fact, we were motivated by this. I think it would be nice to represent points in this new kind of representation in order to obtain better methods also related in the optimization area. So I think there are a lot of things that we can do also in the topic related to optimization algorithms.
Mm-hmm. I think maybe you can have simpler models for the same problem, but in higher dimensions from what you expose it there using this other space, right?
Yeah. Because here what we see is that we could simplify the representation of isometries. Yeah, because we have now a matrix in dimension 5, but we have a matrix that is orthogonal. So this could simplify the calculation. I think that this was the first step in order to obtain this kind of representation, and mainly to check that the computing of the Euclidean distances are more efficient. And now the idea is how to use this in other problems in a more specific way, and also to try to produce codes that are more efficient. I think there are a lot of things that we can do now with this kind of the representation of points now in 5-dimensional space.